Hello, everyone. Thank you for coming to Scaling Python Analytics. We're going to take a look at some pretty interesting stuff, how to scale your NumPy scripts, how to scale your Pandas scripts, how to scale your Legate Boost training algorithms for machine learning. My name is Daniel. I'm a technical program manager for the CUDA Python team. I work in the many Python libraries that we have in order to scale CUDA from single node as well, just core CUDA kernels, up to like thousands of GPUs, and that's what we're going to be taking a look today, which is distributed analytics. So what you will learn by the end of the talk, you'll learn to run how to take an existing NumPy script and run it in not only a single CPU or single GPU, but how to scale it to single node, multiple GPUs with basically no code changes and many nodes and many GPUs, up to like tens of thousands of GPUs if that's something that you have access to these days. The second thing, you're going to learn about how to use Legate DataFrame and Legate Boost to scale more like ETL and machine learning analytic pipelines. So hopefully the name of the libraries give you an idea what they are. DataFrames on top of Legate and boosting algorithms on top of Legate. And we'll take a look at what Legate is a little bit in a minute. And how the Legate Python libraries allow you to scale, like I said, from single CPU, Mac, Windows, whatever you have locally, you can develop there. You can take that and scale the same script into a single GPU, for example, a DGX Spark, the little golden new thing that we're selling, or like any graphics GPUs, one of the more data center GPUs, H100s, and if you have a DGX machine with multiple of those, you can still use those. And if you have a data center or a supercomputer, you can use the same libraries and the same code with basically no code changes, just a little bit like how you deploy it. And we'll take a look at all these details. We'll see how you can keep doing the same functionality you're doing these days, like data cleaning, feature engineering, linear algebra with NumPy, Monte Carlo simulations, optimization, solving of equations, all those different things. You have the same APIs, and you'll be able to scale those to like terabytes and even petabytes of data, right? That's the important thing. So I wanted to ask, how many lines of code do you think you need to change today without any of the stuff that I'm going to show you if you need to take a NumPy script and run it on one GPU? Right? That's a question that is pretty common. You could do that actually pretty easily to a single GPU using CuPy. You can just change the NumPy import to CuPy, and in a single GPU, that has a really good chance of working, right? So what happens if you want to do multiple GPUs? Now, CuPy is a library that is only single GPU, so you are not able to leverage that to do that. You might need to start doing manual chunking of your data that you're reading, your Parquet files, HDF5 files, and it's not really easy. And what happens if you don't have multiple GPUs? You only want to escalate to multiple CPUs. That's something that today you can maybe solve with Dask. You have to like start using Dask DataFrames, or maybe using Spark for the Spark DataFrames as well. It really changes the workflow that you have today, and maybe they're not the system that you like working the most. You like to write very core CUDA, core Python code, native Python code, and you don't want to deal with the distributed systems interfaces, right? So the important thing is, like, from CPU to GPU, it's actually pretty easy these days. For example, for boosting algorithms, you can do Legate Boost, and they have really good support for that. We'll take a look at that later. For DataFrame stuff, we have in the Rapids team cuDF Pandas, so it's basically a drop replacement, an accelerator for Pandas. And even from Polars, now we have, again, from the Rapids team, many ways to scale that. Even for like single node multi-GPU, they don't have a story yet for like distributed multiple nodes, basically, right? So what if I told you that you can actually reduce drastically the amount of lines of code that you need to change? You still need to think about the deployment of the system, of course. We cannot really solve anything with like a magic wand. But at the actual logic, at the actual mental model that you have to keep in mind is the same that you do for like single CPU that you're used to with all the Python libraries in the PyData ecosystem, right? So I'll start with this. If there's one thing that you take out of this session is that you can take a NumPy script, change the import. So instead of doing import NumPy as MP, you can do import cuPyNumeric as MP. And most of the time, this is going to run, right? And if you want to run it in, for example, in my Mac, I just do Python, my program.py, and it runs on a single CPU. Totally fine. If I have a GPU of a server with 4 GPUs, for example, I change the execution command. I do legate --GPUs 4, and it's going to use 4 GPUs that I have in my system. Same script, nothing really changed, and it started to leverage the GPU for computing. And if I have multiple nodes, I just need to basically run the same command in many nodes, and it will take care of like communicating between those, do all the data shuffling, the data loading, partitioning. You don't have to think about any of that. In this case, I have an example running with Slurm, so srun-n10, so 10 nodes. You can put more flags if you want. Run the Legate command, 8 GPUs. My program, in this case, it will run in 80 GPUs, right? Important, you don't need to use GPUs. You also have CPU support, right? So you can do like, for example, 10 nodes, so distributing 10 CPU nodes as well. Which is something that we don't advertise as much, but I think it's pretty cool. A lot of people don't have access to thousands of GPUs, but sometimes they have access to thousands of servers, for example, in AWS. So it's something that we can scale as well. And once you get access to GPU, you can use that or use that for one part of your pipeline. Usually people do it for like the machine learning pipeline in XGBoost using Legate Boost, right? Okay, so before we continue with the other libraries, I wanted to talk about want to make clear what these libraries are and what they aren't, because they sound complicated and people tend to get confused a little bit by those. So cuPyNumeric, first thing is not a drop-in replacement for NumPy, right? So don't expect that everything is going to work 100% the same, especially when you go distributed, right? When you go in a single node, things mostly stay the same way. You can use matplotlib, you can pass it to scikit-learn. We have decent support for the array API, even if it's not complete. But things that when you go distributed, the way that the distributed engine works, you're not going to be able to just pass a cuPyNumeric array to matplotlib and plot that. That's not going to work 100%, right? Because it's a distributed array. Yeah, you're not going to be able to plot that natively. You have to convert it to a NumPy array, which is something that a lot of people do. But cuPyNumeric does implement the NumPy API. So the high-level APIs that people really use day to day, we implement all of those. So most of the times you just change and import if that's what you want to do. I recommend, for example, to keep both. I recommend to keep the NumPy import and import cuPyNumeric as something else, CN, CMP, and use both of those as the program, as you're developing the program, right? It is not cuPy, right? It has similar name, cuPyNumeric and cuPy. Like I said before, cuPy is single GPU. It's a completely different project. cuPy is not owned by NVIDIA. cuPyNumeric is an NVIDIA project. We support the development of that and the whole stack that is below that. Like I said, these don't have array API compatibility. That's like a Python and NumPy API for that many of the libraries that use NumPy, like scikit-learn and matplotlib and all the libraries use that as a way to, pass the right information from NumPy, the data to the compute that they do. We don't have full compatibility with that yet, but we will have in the future. Legate DataFrame. It is not like the drop-in replacements from the Rapids team that some of you might know. So it's not like cuDF pandas, it's not like cuDF polars. It is its own implementation, right? It does use cuDF, of course, behind the scenes, but it's its own implementation of distributed compute of data frames. Works in CPU, works in GPU using cuDF. And right now we also have a polars API. So the default API is more like cuDF, or is more verbose. It's not the nicest one, but now we have a polars implementation of that as well. We'll take a look at an example. Legate Boost is boosting algorithms implemented on top of Legate. Hopefully that's kind of clear. You can think about an XGBoost or IGBN replacement that is multi-CPU, multi-GPU, and all the combination of those. All the libraries in Legate are CPU and GPU native. Again, really important. We talk a lot about GPU because that's when you get a lot of performance improvement. But like I said, this also works in CPU, and I think that's kind of nice. You're able to keep your NumPy and pandas or polars or XGBoost mental model, right? So it's basically you're executing every single line of code. So the way that you execute is like you expect it. It's not like Spark where it's lazy loaded and you can optimize a little bit more sometimes, but the execution is not what you were expecting from a regular Python script. It is Python, which is important because some people get confused sometimes. There is like other languages that claim to be Python, but they are actually not Python, and they tend to like say, oh, we optimize CPU and GPU and distributed stuff, but then you have different Python syntax and stuff like that. They mimic some of the Python APIs. This is actually like a Python library that you install. It's the same Python runtime that you use. So you install this from Conda or PyPI as you would with any other library. Of course, there's a C++ library behind that. Many libraries actually below that, but we use those. So it's actual Python. It's not like other languages that are out there. And the other important thing is that it's optimized for scale, right? So if you have some data set that you know is never going to grow beyond a couple gigabytes and you can process totally on your workstation, you might not need this, right? It's going to run. Yeah, we support that and we do a lot of examples with that. but it's optimized for scale. It's optimized for like the thousands of GPUs. Well, you don't have to get to thousands, but like many GPU scale, basically. And that's where it shines. Okay, so I mentioned this a little bit briefly. I can go from like my laptop, single CPU, that's what I do my local development, import cuPyNumeric, load my HDF5 files, do my data munging, whatever, import polars, read my Parquet files, I develop maybe with a small subset of data. If I have a DGX machine, because I was looking, I wanted in the raffle of GTC DC, I can do that there. I have, for example, 2 4090s that NVIDIA provided to me, and I do that in my local workstation, and I have 2 GPUs, and I distribute work there between those two very easily, right? That's the second part, that's the accelerated work, so actually using GPUs. Then when you go to like multi-GPU servers, like a DGX machine with many H100s or Grace Hoppers, you can also do that, same code. Just different execution a little bit, the execution command. And if you have access to like a supercomputer, you can scale to like I said many times, hundreds of thousands of GPUs, hundreds of thousands of nodes. Okay, before we go to like the other libraries, let's talk a little bit about how the stack works. Hopefully, most of the times you won't need to see any of this, but you know, things happen, and you'll see some Legion error, some Realm error every now and then once you're trying to execute this. In the same way that you do a Spark, you're going to see a JVM error. Nothing you can do about it. Once you go to multi-distributed nodes, like you're going to see this type of things. But Legate is our composability layers to develop all the libraries. So all the libraries, cuPyNumeric, Legate DataFrame, and built on top of Legate. That Legate uses Legion for the parallelism. So that is the task-based execution engine, basically. Similar to like Spark and Dash, they have like these graphs, whatever. That's what Legion does. And Realm is the actual execution, the one that's actually executing. So it does like, takes the chunks of the data that Legion passes and executes those in either CPUs or GPUs, right? So it's agnostic of those things. And again, we can target heterogeneous architectures of like from single nodes to supercomputers, right? So just some details there. And then we have many libraries implemented on top of that, on top of Legate, right? So we have cuPyNumeric, Legate Sparse for like SciPy sparse arrays, Legate Boost, Legate DataFrame, and Legate IO, which is very important, right? Look, so you have, how do you read and write many files and file formats? And a little bit more details there. I don't want to spend that much time here. Is how this actually works to like execute the task, right? So you have your script, you import these libraries, you write your code, then Legate takes care of like looking that and converting those APIs to tasks. And the Legate runtime optimizes that. You have seen this a million times with the Spark and Dask. There's a small difference here. We don't optimize the whole graph. We optimize basically layer by layer, right? So it will be like, for example, from the A circles to like BCC, right? So it will optimize layer by layer because we're actually executing as the program goes, right? That means that sometimes we cannot do the most optimization for like some data movement, but we're sometimes also able to bypass that with some of the query optimization from polars, for example, right? So there are many ways to optimize these things. And you can also tell Legate some hints about the layer of your data and whatever to help optimize some of these things, right? Okay, so Legate DataFrame. Hopefully the name gives away what that is. Is a DataFrame implementation on top of Legate, right? So this is the naive base implementation of the API. You see at the very beginning, I import Parquet read and Parquet write because I'm going to read Parquet files and I'm going to write Parquet files. I import a join operation and I import some binary and date manipulation operations, right? What I'm doing here is a join of those two Parquet tables. So very, very simple. This API mimics the cuDF API a little bit. It's not the nicest, like this binary operator and like these extract timestamp components. It's not the nicest APIs. But like I mentioned, now we have a new polars API. So this is the same code that I had before. In this case, because it's just a join, doesn't change much. But you can imagine as I have more complex queries, the polars API is nicer to use. So I import regular polars, and then I import our polars execution engine, basically. That makes a hook into that. And at the end, the only thing that I change is instead of like doing data process.count.collect, I do data process data.count.legate.collect. So that Legate is going to use Legate to execute that particular query. We don't have support for the full pandas, for the full polars API. We have support for a lot of it. we're able to run all but 2 TPCH queries. And once we are able to run all of them, we'll probably make a blog post announcing that and some benchmark numbers that we have. But today you're already able to do a lot with this API. Especially when we go to the streaming functionality, which is the autocore functionality that I'll talk about later. That's when it gets a little bit more tricky. But we'll eventually implement everything and do more benchmarks and more APIs like TPCH and TPCDS. Again, very important. The code stays exactly the same. You have to just change the way you call the code, right? So in my local development, I just do Python program.py. It runs on my CPU like it runs with pandas. Same thing. In the 2 middle squares, right? If I only have 1 GPU, I can do Legate -GPU1. I actually just ignore it. It will take all the GPUs and run it in my program, and it will run it on that GPU, right? I can, for example, also say like, hey, only use 50% of my VRAM of my GPU, right? I can tell that. And if it doesn't fit, it will crash, but you will just respect that, right? Same thing, if you will have single node multi-GPU, you don't have to change anything, just Legate -GPUs8, and it will use all the GPUs to distribute the compute. So if your data doesn't fit on 1 GPU, you can use more GPUs. And then when you get to like the multi-node cluster, you need an execution engine. I have example for Slurm, but we have support for many other things like Kubernetes or whatever. We'll talk about that at the very end. I can tell it like running 10 nodes, 8 GPUs, 80 GPUs in total, and it will run the code execute the code in those. So very, very nice. And again, one thing here I don't mention here, and I should have probably, is multi-CPU support. Again, you don't have CPU, you have GPUs, you can do it in multi-CPU, and I think that's pretty cool. There is no, currently that I know, an open source version of like distributed polars, right, for CPUs. I think they have one in the private offering that they have in the cloud, but open source, there is no one way to distribute polars in CPUs. So actually, I think that's pretty cool. One of the nice things that we usually don't talk much, but you can scale that pretty quickly using Legate DataFrame. You can think of that as a distributed Apache Arrow execution engine in some ways as well, which is pretty cool. It's an open source version. Yeah, everything here is open source, of course, and you can download it today. What happens? I mentioned that if I restrict my VRAM on my GPU and I have too much data to load, it's going to crash, right? That's not ideal, but that's something that happens. There is a lot of large data sets. Sometimes I don't have, or most of the time, I don't have enough GPU memory to load those data sets. That's where we have this streaming mode or out of core mode, basically. So if you are familiar with Dask and Spark, it works in a similar way. It's not, so the code inside basically the only thing I need to change is create this Python context manager, right? Which is this with the scope, parallel policy, blah, 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 streaming. I enable the streaming and I over-decompose my computation, in this case by 64, right? So if I have very big Parquet tables, it's going to chunk those tables, respect the row groups and so on, do the join, and then at the end, I'm writing a HDF5 file, right? So chunk by chunk is going to read the Parquet, do the join, do whatever it needs to do to like do the join correctly. Sometimes you have to recompute or whatever, and write HDF5, an HDF5 array, a file which represents the array that I can load later in Legate Boost, which is what I will show in just a moment, right? But that is the way that you can go beyond, like you can compute a lot of data in a single GPU or multi-GPU, right? The more GPU memory you have, the better. But if you don't have enough to load your terabytes of Parquet files, you can use this streaming mode. And this is new functionality that we have developed with some of our customers that do this. One thing here, like some of this, most of the time here, like depending on like how like close to like a regular CPU deployment you go, you won't get as much benefit, right? Like I said, these libraries are optimized for scale. They're optimized for like you're able to load as much data as you can in memory, in GPU memory, and execute very quickly on those. But I've been able to process, I think the last one I did was 17 billion rows of Parquet file in, I don't remember 100% if it was 1 GPU or 8 GPUs, but it was a single node. There's no way that fits in a single node, and I was able to process that like in 10 minutes. So it's pretty impressive, right? Training an XGBoost model, not just doing the join, so doing like both things. So something very nice. Legate Boost, okay, so that's the next library. Hopefully the name gives away what it is, boosting algorithms implemented in Legate Boost. And if we go back to like the first question that I asked at the very beginning, like how many lines of code. You don't need to read this code. It's intentionally small. How many lines of code do you need to change today to scale XGBoost training, right? The most popular library and one that we support at NVIDIA from the Rapids team is the XGBoost, right? So on the left, we have the single GPU, and that's super easy. You just have to add a parameter, device equals to CUDA, and it will utilize that GPU. And if you have multiple GPUs, do CUDA colon the device that you want to target, like as an index, CUDA colon 0, CUDA colon 1. That is for single GPU. What if your data doesn't fit in your GPU, like we saw before with the streaming, right? That's what the XGBoost external memory feature that I think they introduced that in 3.0 does, right? So you have to write an iterator and you have to chunk the files that you're reading and pass them to XGBoost. And I mean, it definitely works, right? I just had to write a lot more code, and I have like ... in many places here. It's not even the full code, but I had to add many lines of code compared to my first example, right? What if I wanted to do, and that's also for streaming, not auto core, but also some single GPU. If I want to do a multi-GPU in a single node, I need to add even more code. So this code is also code that is not there. So you can basically add those lines of code and even more that I don't even complete it here to do multi-GPU training on a single node, right? They have a lot of examples. Basically, the way this works in XGBoost is a multi-processing sync, and you're able to train those things. And if you want to go multi-node, you can use something like Dask. But in Dask, one of the requirements today is that you need to feed the input to XGBoost in distributed memory, right? So there is no auto core. But you can see there's many ways to do this in XGBoost. You need to learn all of them. You need to develop all of them and debug all of them, right? In Legate Boost, there is only one way to do it, and the only thing that you have to change is the way that you execute it. So this is the only code that you need to do. It basically mimics the scikit-learn API. I generated some random data, and I passed them to this regressor, right? I don't have the full, like all the variables here, but that's the idea that you can take off, right? Import cuPyNumeric, import Legate Boost, and pass the data there. I have some benchmark numbers about like scaling. This is weak scaling of just Legate Boost. Basically, we have 20 million columns per GPU. And then we go from like 8 GPUs to 1,024 GPUs. And you can see that for most base models, the weak scaling is kind of linear at the end. It kind of explodes, which makes a lot of sense because of all the communication that is happening on the cluster, right? But you can see, again, the only thing that you need to change in the code is how you call it. So single CPU, Python train LB.py, single GPU, Legate GPUs 1, single node multi-GPU, GPUs 2, and then multi-node version, you can do SLORM. That's the one that we use the most, but you can do it in many ways. Just call the script multiple times, and it will just communicate and work out of the box. Then I have like a little bit of code here, like how does it look like for a full pipeline, like full analytics pipeline, right? Like all the individual libraries are nice, but they are composable. They're all developed to work together. So I can, for example, load data using Legate DataFrame. And this is the job that I showed a couple of times, so you don't have to read that again. But then I can convert that to cuPyNumeric arrays, and I can pass those cuPyNumeric arrays to Legate Boost in the same way that I could read from pandas, convert to NumPy, and pass those NumPy arrays to XGBoost. Similar ideas. We want to match the mental model that people know and like from Python and the PyData ecosystem today, right? So same thing. What happens if I want to do like a stage pipeline, right? Like I have a lot of data that I only need to pre-process once and then train multiple models, multiple XGBoost models, Legate Boost models based on that. I can just use Legate DataFrame, like I showed, read data, join, do whatever, filter, group bys, whatever I want to do. Write to HDFI files as an intermediate file, and then do multiple training passes in XGBoost and train many, many models. Okay, so deployment. This is I talk about like, hey, the code stays the same, but deployment, you have to think about it, how you actually distribute the execution, right? So the deployment of all these in multi-node requires MPI for now. That's a dependency. We use it for some very like initialization of the processes. We're actually working on removing that dependency, and it will come in the future. I showed a SLORM, and a lot of people tell me that they love a SLORM, but I don't think anybody ever told me that they love a SLORM. People use Kubernetes, right? And they want to do it in the cloud. So we have Docker containers, and we have Python packages, Conda packages. We have everything, so you can build this yourself and deploy it. In Kubernetes, for example, you need today the MPI operator, which is not ideal, and I get it. That's what we're trying to remove that dependency. Eventually, we'll have like a more IP port type of thing and scheduler client architectures. Right now, you need to do it with NPI, mostly because most of our customers are HPC customers. They have that already, and it's something that is not that hard for them. You can use this today in the cloud. Like Coil is a cloud deployment company. They started doing DAS deployments, but they do many things now. And you can actually run this using their NPI command. So you can do Coil NPI run Legate, and it will actually, they have a VM basically with all the dependencies, and they take off like doing this. And it runs in your AWS account. So I know a lot of people run this in the cloud, and you can do this. One nice thing, I actually run these multi-CPU, multi-node polars, right? I'm super excited about it because I always wanted like a multi-CPU thing that was easy to use for data frames. This actually runs in the cloud today using code, but everything works, of course, Legate Boost and whatever. Okay, so we had a couple of extra sessions. We talked a lot about cuPyNumeric in the previous session. So if you missed that, there is more details just about cuPyNumeric and the use cases that we have been able to optimize with that. We had CUDA Python kernel training. So if you were there, thank you. And I think you can also catch those later as well. We have the Connect with Experts just I think after this session. So I'll be there if you have more questions about this or just any CUDA Python questions as well. We also had the CUDA 13 features that was I think today as well. If you missed that, that's really good to see all the new actual core CUDA stuff. How do you get started with this today? You can just go and install it. That's the easiest way. It's just a channel, so -c Legate, and all the libraries are there. cuPyNumeric, Legate DataFrame, Legate Boost. That's the easiest way to do it because it includes like the CUDA toolkit and all the things into that environment. We also have API packages, so you can just install NVIDIA cuPyNumeric and it will be there. Again, you can just run this Legate -GPU1. So if you have one computer with one GPU, you can just try this and let me know how it goes. And we have documentation for all the libraries as well there. I just want to invite everyone to join us in accelerating the Python computing. We believe it's really important to take the ecosystem that people like, that people are running infinite amount of jobs these days using the libraries that they like. And we want to be able to accelerate for the whole broad spectrum from single CPU, multi-CPU, GPU, multi-GPU, multi-node multi-GPU, and all the combinations that you can think of. So try it and join us in this journey. Thank you.
Quick question on the out-of-core training or out-of-core processing.
Yep.
Is this only supported on the Grace Hopper and Grace Blackwell architecture or regular Blackwells? Okay.
Yeah, the regular, you don't need Grace Hopper to do that. I think it helps a lot with the unified memory. If you have something like that, it helps a lot with that type of thing, but you don't require one of those. I do this on my regular x86 chips and GPU chips,
Cool.
Thank you, Daniel,
Thank
for such a wonderful session today.